I guess today I'll talk about kind of something I've been thinking about for a while, which is like the work I did here when I was at Lids was to think of making algorithms that are robust to bad training data, in the sense of making custom algorithms that work really well when the data is bad. And that's not always tenable, right? Sometimes you have to work with the algorithm you have given as opposed to inventing an algorithm that would be great. And so today's talk is about taking an approach where you don't have that much freedom to change the algorithm. So what can you do? Okay, so let's get started. And obviously, you should stop me at any time if you have questions. Okay, so just a brief bit about motivation. Like I was going to put an overview slide of how AI is taking over the world, but I think you've seen that. Okay, so I just kind of maybe focus in on a few trends, right? So one of the trends obviously is that machine learning models are getting larger, which means that they have higher accuracy, and it also means that they are harder to design and train from scratch, right? So like for example, if you take one of these bigger models that people use for ImageNet, or you take the latest BERT XL model for NLP, these are things which I don't think it'll be pretty hard to train in academia, for example, right? And so the upshot is you need lots of computing, you need lots of compute power, you need an enormous amount of training data, which often does not exist outside corporate America. And even after all that, the actual architecture design is a lot of art and not science, and also a lot of like work and hyperparameter optimization and things like that, which is not easy to replicate. Okay, so what often happens in practice, and I think what 90% of the people who work on neural networks do, is fine tune, right? So you take a model that already exists, and you modify it to some extent, right? And the extent obviously differs on the person, and differs on the application, right? But the idea is that you first train a large model, and typically nobody does step one except maybe Google research or something, right? So you train a large model, which is quite difficult to do, needs lots of parameters and so on, right? And on some kind of generic task, right? And once you have done that, you take that model and you replace the last few layers, or you change a few parameters, or you make a few architectural modifications, and then you run it on your data, which is much smaller, but that's fine because you're starting from a good place, right? So you kind of have the high accuracy you get from the general task, but you're able to specialize it to your specific task, right? So this is what often happens, right? And the way we specialize is typically by downloading a model from the web and using TensorFlow, which means that you are taking a few stochastic gradient steps on a pre-existing model, maybe with some changes in parameters, changes in the final layers or something. Okay, so the advantage of this is that you need relatively little data to get state-of-the-art results on your special task, right? Like there are many places where people do this. People do this in transfer learning, meta learning, and so on. Right? And so we're going to peer a little bit into what happens with this kind of data pipeline, where I take essentially somebody else's model and I train it on my own data. What if my own data was bad? Right? Will I still retain the accuracy of the old model? That's the question we're trying to answer. Okay. So unfortunately, the answer is not so great. Right? So if I take a model like a ResNet, for image classification, and then I want to say, use that to classify thousands of breeds of dogs that I have, right? If I have very nice labeled data, it'll work great. And if I do not have very nice labeled data, the performance will drop precipitously. Okay, and we'll see examples of this, right? So I'm going to talk about bad training data in a kind of loose sense, right? But there are, kind of at a high level, we can think about three different kinds. One is there is adversarial errors in the features, right? So people are changing pixels in the images, right? So that is super hard, right? There's been a lot of interesting work on it. I am pretty much not going to talk about that kind of error, okay? That's kind of the hardest kind of error to deal with, right? And then somewhat easier is adversarial errors in labels or systematic errors in labels. Right? So it's like nobody is jimming with the image, but just that some images are badly labeled. This is quite common, right? In any kind of mechanically tucked data set or something, you're going to be a lot of errors, right? And the final thing is that nobody set out to create errors, but there were just errors because of sloppiness in data. Right? So we'll primarily be talking about the last two kinds. Right? But it is also, the first kind also is very interesting, but it needs very different solutions. Right? Actually, a lot of work on this has happened in MIT itself, but I'm not going to talk about it. Okay, so let's take a few example cases to see what to kind of understand what I'm talking about. Okay, so here's the CFAR10 data set. I'm sure you've seen it before. It's the second most popular after the MNIST data set in terms of academic talks. Okay, so there are a bunch of images from 10 classes, right? And there are 50,000 images, and there are 10,000 test images in the original thing. And the idea is when you get a new image from the test, you have to learn to classify it in one of the 10 samples in 10 sets correctly. Okay, so you can download this architecture from the internet, right? This has hundreds of citations, must be good, right? Let me download it, right? And let me train it on CFAR10 from scratch, right? And this is a small enough network that I can actually do this, right? On a few GPUs, and we get 92% accuracy. Right, so the actual paper has higher accuracy. They did more, kind of search and training and so on, but 92% is pretty good, right? So because the point I want to illustrate is not the 92%. Okay, so this is a kind of a good model from the internet. All right, now I want to fine tune it. Sorry, I don't want to fine tune it. I want to see how robust is this model. Okay, so what I'm going to do is I'm going to take a small fraction of the labels, and I'm going to change them in my training data, right? So I'm going to take 20% of the things that should be labeled horses and label them birds or label them trucks or something like that, right? I'm going to make label errors in my data, but not too many, right? The majority of things labeled horse is still a horse, but some of them are not horses, okay? So, and now we can ask what happens to the accuracy of the model, right? And the answer depends on how you made the label errors. If I take horses and change the label uniformly across all the other labels, then it is still fine because the data set is so big, right? So data set size can come to the rescue when your errors are benign, right? I just made random errors in my labels. There is nothing else that seems convincing enough to confuse the model. So even though there are errors in the data, if you plot the size of the data set on the x-axis and the accuracy on the y-axis, right? The curve I'm talking about is not in the plot, but it would be something that starts out low and turns up high. On the other hand, what I am showing here is what happens if you have somewhat more systematic errors, right? So every time a horse is mislabeled, it's mislabeled as a bird, right? It's still only 20%. So like 80% of the images labeled horse is a horse, but 20% are labeled bird, right? Now this is a harder kind of error, right? But it's still not unreasonable, right? If there are two things that are confusing to humans, it's very likely one will be labeled as the other. Okay, in that case, the size of the data set cannot come to your rescue. Okay, because this is a plot that shows that for the CFAR10 thing, right? So we use pretty much the entire data set in terms of training samples. We use 50,000 samples, right? And the two curves on the top are essentially if we knew the correct labels, and the one at the bottom is what happens when you have 25% label noise, right? So the accuracy drops by kind of more than 25%, and then it never recovers.
Again, it's 25% is systematic.
25% is systematic, right?
Not like random.
Yeah, so if it was random, then you would have a curve that would start at the bottom left, but go to the top right, right? So random label errors are quite benign, at least for this problem. Okay, so the question in this case is, if we knew that 25% in each label were incorrect, could we do something different, right? And by doing something different, I don't mean making a machine learning model like ResNet 16 from scratch, because that is actually pretty hard to do, right? But it is about changing the way we train it, right? Okay, here's another example, and this is for generative models, right? So the previous was a discriminative model, it was a classifier, right? This is a GAN. For those who don't know what a GAN is, it's essentially a neural network which takes in a random vector, let's say of size 100 in this case, right? And has a bunch of feed-forward layers, right? So it kind of keeps expanding the dimension, but in a structured, systematic way, right? To finally get a pretty large output. For example, it could be an image, right? So I can put in 100 length random vector, and I'll get a random image at the output, and I can keep doing this, right? And the dimension space of the output is actually the dimension space of the input because it's a deterministic function, right? But it somehow, if you train it right, it can traverse the manifold of the images you want, right? And the images you want are what you have trained it with. So in this case, I, or actually the DC GAN paper, so not me, right? They trained it with the MNIST training samples, right, which are these handwritten digits. And so now, they essentially made a network where I can give a 100 length Gaussian vector, and I'll get something that is one of these that's one of these letters as an output, one of these numbers as an output, right? Every 100 length vector that I put in with high probability will look like a handwritten digit. Okay, so this is the GAN. Okay, and this is also not our work, right? This is a kind of pretty famous one of the original GAN papers, and it has the ability to generate completely new handwritten digits, right? So that is actually the MNIST data set. This is generated, and it looks pretty high quality. Okay, all right. So what happens now if you have sloppiness in data, right? I think I'm training my GAN with handwritten images, handwritten digits, but suppose some of my images are not handwritten digits. Suppose they're pretty far from it. Okay, so in this case, the reason I chose MNIST is because it's convenient to get the alternative data set. So there's something called Fashion MNIST. Okay, Fashion MNIST was made, so it's again 10 classes just like handwritten digits, but they are actually little black and white images of clothes. Right? And then there are 10 labels like coats and shoes and so on, right? And the idea is that if you there were a million papers written on MNIST, and the idea is that if your algorithm is actually good, you should be able to run the same algorithm on Fashion MNIST, and you should get the same accuracy. And obviously, half of them didn't get it, so that's why it became famous. Okay, but for our reasons, it's convenient because I can just plug it into the data pipeline. Okay, so here's a simple kind of proof of concept experiment, right, which is that I have 80% of my data being handwritten images and 20% of my data looking completely different, right? There's like Fashion MNIST. Okay, but I mix all this up, and now I don't know which is which, right? At least I don't know a priori which sample is a Fashion MNIST sample or an MNIST sample, and I follow the same procedure, right? I do the same training of DC GAN, right? With the same thing as before, and then I take 32 random Gaussian vectors, put it through my newly trained GAN, and see what happens, right? And it looks like pretty bad. Okay, like many of the things don't look like handwritten digits or clothes, right? Like it would have been fine if I generated clothes some of the time and handwritten digits some of the time, because that's what the data is, right? But the thing is that these are far enough away from each other that something like DC GAN cannot do this. Okay, so it just mixes them up, it gives low quality results. Okay, so this is an example of sloppiness in data, right? If you have sloppy data, then if you run it through a generative model, you train a generative model with sloppy data, you'll get sloppy results, right? And so here again the question is, if we knew that 20% of our now unsupervised training data was wrong, came from or was spurious, what could we do to learn differently? Right? Okay. ML models, whether they are neural networks or not neural networks, right? But ML models trained for a particular task in mind are typically out of the box not going to be robust for when the data doesn't follow the assumptions, right? So a better and more principled approach, right, is to actually design a custom robust variant, right? That's the right thing to do, right? Like, there's all this paper on robust regression, there's papers on robust PCA, robust subspace clustering, right? And there's like this beautiful line of work, you're using deep algebraic insights to solve these problems. That's the correct way to do it. Unfortunately, we are now in the world of neural nets, and we cannot really do this, or at least I cannot, right? So it's often untenable nowadays, right? Because state-of-the-art results on clean data problems come by models that we don't understand at the same depth, right? And so it's hard to design a new model that does both things, is robust and works as well on the clean data, right? Like tomorrow, if you come up with a model that is 80% accurate on image classification, but is also robust, I assure you nobody will care, right? So that's the problem, that's the issue, right? So yeah, so we are kind of stuck with the models we have, and all we can do is jimmy around the edges, and the question is, how do we do this? Okay. So can we make any machine learning model robust to bad training data? Okay. That's the motivation, by making minimal assumptions on what we can do. Sorry. Okay. So we call this model agnostic, right? You kind of want to get robustness for a pretty broad class of models. So what is this class, right? So what is the basic things that most machine learning methods allow you to do, right? So what they allow you to do is that you can train or retrain or fine tune a model on a bunch of samples, right? You can, like most machine learning methods will come with a training algorithm. So that's one. And the other one is that for any given set of model parameters, most machine learning models will give you a per sample loss, right? So if I was learning, for example, linear regression, and then I gave you a new xy pair, right? You could look at the regressor, you could look at my x and y, and you could find out the error. So that's the per sample loss for linear regression, and neural networks also have a per sample loss, right? So pretty much any machine learning model has a per sample loss. Okay, so these two are pretty much available for most machine learning models. Okay, right? So more specifically, we look at the case where there are samples Si, there is some loss function that depends on the model parameters theta, and you want to minimize, and like the way you would train a model is to minimize this loss function, which is sum over the losses over the samples. Okay, and correspondingly for any fixed set theta, there is a loss of sample I, which is L theta hat of I. Okay. All right. So here's a quote from like 200 years ago, right, which is essentially the motivation for our algorithm, right? So it says that if among the errors there are some that are too large, then okay, blah blah blah. Essentially, you have to ignore them, right? If your data doesn't seem to be correct, and there are some things that have very large errors, it may not be a bad idea to ignore those data points. Okay. So there's this classical statistical notion called trim loss, right? And what it says is that, okay, so the standard approach for model learning is what I just wrote before, is that you want to minimize the loss over all samples, right? And so what trim loss says is that instead, let's fit a model only on a smaller fraction of samples, specifically on a fraction tau, and you can decide what tau is, right? If you know that that 20% of your data is bad, then tau is 0.8, or maybe even something less than 0.8 if you're conservative, you mean 0.7. Okay, right? And so now we have a trim loss estimator, which is the argmin of a double minimization, right? You want to minimize over the theta, and you want to also minimize over the set of samples that you even care about, because you are free to not care about 1 minus tau fraction of the samples. Yeah? All right. So it's a pretty simple idea, at least to state, but it's pretty hard because it's a joint problem of selecting the subset of samples and finding the best model on that subset. These two problems are joined and coupled together, right? And so even for linear regression, this is not actually easy to solve in the worst case. Right? It's not possible to solve it exactly. All right. Okay. So looking at linear regression more closely, because that's what our theory results will be about. So the samples are xi and xi yi pairs, and standard training is just to minimize the squared loss, and trim loss is to minimize the same loss but over a subset, right? And this is NP hard. This is not our result, by the way. It was known to be NP hard. Okay. So a simple idea is we cannot solve the joint problem. Let's instead alternate. Okay. So if we knew which were the good samples, we could get a good model, just fit it on them. And alternatively, if we knew what a good model was, we could select the good samples. Okay. So more specifically, right, you first initialize with all the samples, and some of them are bad, right, and then you alternate between selecting a good set of samples. So the way you do that is that you just evaluate the loss on your training data. So you have trained a model on some data, and then you evaluate the loss of each sample in the training data itself, and then select some, right, and then you retrain with that smaller fraction. Okay. And then retraining is standard model fitting. Okay. So this is the method. You can apply it to anything, right? Okay. Okay. So what I'm going to present now is some theory results and some experimental results. I'll provide theory results for things for which we can do theory with, and we'll provide experimental results for what people do experiments with. But unfortunately, they're not exactly the same, because I don't have theory for deep neural nets. It's an interesting problem if we can make one, but as of now, we're going to look at we're going to show linear convergence to the true model for mixed linear regression, and I'll specify what that is, and then we're going to look at some results for kind of the things I motivated before, which is the deep image classifiers and generative models. We also have results for something called backdoor attacks, which I'm not going to go over, but I'm happy to discuss offline. Yeah. Okay. So I'm going to step into the mixed linear regression problem. Right? So in mixed linear regression, the idea is that you have a bunch of samples, but they come from more than one linear model, but you don't know which linear model they come from. Okay? So there's a theta 1 star, a theta 2 star, and blah blah. Maybe there are k classes, right? And you have samples which are xi yi pairs, but each sample comes from either the first equation there, which is yi is the xi transpose theta 1 star, or it's yi being xi theta 2 star, or so on. Right? So we don't know which one it comes from a priori. Right? And so this is like a simple instance of the bad training of systematic error in training labels. Right? If you imagine that there are two classes, and 80% of the samples comes from theta 1 star and 20% comes from theta 2 star, right? Then this is an example where you think everything comes from one model, but actually 20% comes from a different model, right? And theta 1 star, for example, could be your parameters for classifying whether it's a horse or not, right? Okay.
So here you're modeling the bad data as the alternative mixture components.
The alternative mixture components, right? So there is one mixture component that's good, and everything else is bad, but the bad has structure, right? Yeah.
And so somehow you'd like to argue that this theta 1 star versus the other thetas are not too close otherwise.
Yeah, yeah. So whether we can recover theta 1 star or not will depend on how close these things are. Yeah. So what is iterative? Okay, so this is ITLM. ITLM is iterative trim loss minimization. Okay. What does ITLM do? What ITLM does is it pretends that a fraction of the data came from one model, right? And it doesn't care about the fact that there were other thetas. It actually doesn't even need to know how many other thetas there were. Okay. It's kind of running after one of the theta stars, right? So we need to fix a fraction that we care about. Let's say there's tau, right? So it find the tau n samples with the lowest loss, and then do least squares on these, and then repeat. Okay. So the algorithm is I start from some theta 0, right, and then I keep iteratively updating it by finding the samples that are close by, and then refitting only on those samples. Okay, so let's see what it looks like in the picture. So suppose I have red and blue samples. So I've just marked them red and blue to show the true model which it comes from. Right? In the actual data set, we don't know what is red, what is blue. Right? If we just do a least square on the overall model, and tau is bigger than 50%, right? If that's the case, then we'll get some line that looks like this. Right? And what do I mean by looks like this? It means that it has more red points than blue points. It does have some blue points, but it has more red points. Okay? And so now when we fit it again, we have triaged more blue points than we have red points, and now we have, in the second iteration, we have even more red points. Okay? And then in the third iteration, we have even more red points, and so on. Okay? So this is kind of like a proof by picture of why it works, at least for mixed linear regression. Right? And there is an alternative setting, which is if these were outliers. Right? And where the blues were just completely arbitrary. And even if they were completely arbitrary, a similar picture could be made to hold, provided the reason is that either they would not throw off the problem that much, and if they did throw off the problem that much, they would have very high loss, and then in the next step they would be triaged out. Okay, so so here's the informal theorem. Right? What the informal theorem states is that, okay, so let's decouple two things. One is how we initialize this iterative procedure, and the other one is what does it do once it's initialized. Okay, so let's say we start from some theta, right, and then so if I start from a particular theta, as far as we can show, we will only linearly converge to the closest one, and even that may or may not happen, right? But there is no hope of converging to something that's further away. Right? So if I have if I'm looking, so if I have data which is 80%, 20%, and I started closer to the 20% one, well, then it's going to be very hard. Okay, it's not going to work out so well. Right? Even if I start closer to the 80% one, it may or may not work out well. But definitely, if I start close to 20% one, but I'm retaining like 80% of my samples, right? I will not go to the 20% solution, and I will not go to the 80% solution. Okay. Right? So there will be linear convergence to the closest theta star, provided what? So provided that, so one of the things that's needed is that this closest one should have a fraction of data which is bigger than the amount of data that I'm retaining. Right? If I'm retaining 50% of my data, right, but I'm trying to go to Devrat, but he accounts for only 30% of the data, there is no way I'm going to converge to Devrat, even without noise. Okay, right? Okay, so this is the informal theorem, right? And in the papers we have two variants of this. One is kind of deterministic conditions on the x's, y's, and theta stars under which this works, and the other one is simplified conditions for when the features are IID Gaussian. Yeah.
So I have one question. So when you're presenting the last couple of slides, the pseudocode, select tau and the data points, and then repeat. Next one.
This one?
No.
This one?
No. The repeat algorithm. You said select tau and points, and that minimizes the y minus.
Oh yeah.
X,
Yeah, this is.
Or like you said that selecting those tau and points that minimize this loss, the problem that you described as being NP-hard at the beginning?
Oh no, which minimizes the current loss, right? So the NP-hard problem is, like for every set of samples, what is the loss if I could find the best theta for those samples?
Okay, but then it's still combinatorial, right?
Yeah, so that is combinatorial because you have to, because the model is uncertain, the model depends on your selected set, right? But this is simpler. This is just saying somebody has come into the door with a model, you cannot touch that. You just have to find the best samples for that model. So that is just like you evaluate the loss for each sample and then you sort.
Why for each sample? Is it
There is a loss per
each subset of samples.
Yeah, but the loss of a subset is the sum of the losses of the individual samples. Yeah, so a model has to have that. If the model does not have that, then this does not work. But many models have that. Yeah. Okay. Okay. So here's the theorem more formally, right? So if I have a theta hat that's closest to theta 1 star, right, and the fraction tau 1 star is larger than tau, then the next iterate of the algorithm satisfies kind of this linear convergence result, where this is the current error and this is the next error, and this is a constant which we want to be less than 1, and sigma is the variance of the additive noise. Okay, so we can even think of sigma just being 0 if that makes it easier, right? And so we can prove this provided we use, okay, first of all we need to use fresh samples, okay, because there is this weird thing that happens, which is that you have a theta, and if you use x's, if it came from some x's and then now you use the same x's again, then the theta is not independent of the x's. Okay, so there may be a way to analyze it so that you can account for this, but we were not able to do it, right? So, but the kind of cheap way around it is to have new samples, right? So if you have new samples, which again come from this mixture distribution, right? And if you have enough samples, so you need d divided by c square samples, where c is the same constant above, right? So kind of the more samples you have, the better the convergence constant you will get. And then if it uses this many samples in that iteration, then you'll start getting linear convergence to the closest to the closest theta 1 star. Okay.
In your asterisks, you say there exists a counterexample.
Oh no, yeah. So this is not it's not a counterexample. It just says that if the fraction of data that is accounted for by theta 1 star is less than the fraction of data I'm keeping, I will not converge, right? So then this doesn't work. Yeah, it's not a counterexample. That's actually said in the theorem. I didn't need to include that. Yeah.
Can you recover like theta 2 and other thetas?
Yeah, good question. I was hoping nobody would ask that. So the answer depends on whether it's the noisy case or the noiseless case, right? So in the noiseless case, it's obvious, right? So what I mean by noiseless is, if you had the ni's being 0, right? So it's still mixed linear regression, right? So if the ni's are 0, then the answer is easy, because once you recover theta 1 star up to some decent accuracy, you can use it to triage and peel away essentially samples which are from theta 1 star and then repeat, right? Another thing you can do is kind of empirically is you can start from somewhere, like especially if you have many components, doing overall global least squares will get you nowhere, right? You might as well start somewhere random. So once you start somewhere random, you can see where it converges, and if that convergence point doesn't lead to lots of 0 error samples, then the initialization was bad, right? So you could actually initialize several things in parallel and do like some embarrassingly parallel thing to finally find, and hopefully you'll find something that's good, right? Yeah. So if you don't have noise, we can peel and repeat. If we do have noise, we can do like dirty peeling and repealing, but it becomes much harder, right? Like I mean, as you increase the amount of noise, right? So if you see in this theorem, right, the separations didn't come into play, right? And the reason separations don't come into play is if you don't have noise, the separations don't really matter so much, right? And if you do have noise, right, then you are anyway not getting close to theta 1 star. You're not getting that close, right? You're always off by a sigma, right? So you're always off by the noise ball, and anything outside the noise ball can be rejected, but anything inside the noise ball you cannot. But you could not do that anyway, even if it was not in the noise ball. Does that answer your question? Yeah. Okay. Okay. Right. So surprisingly, this simple algorithm gives the best statistical performance for mixed linear regression when there is no noise. Okay. So there has been quite a bit of work on mixed linear regression, including using the EM algorithm, using convex relaxations and things like that. Right. This works better than all of them, with a caveat, which is the resampling. Right. So you need log n resampling to get within 1 by n kind of error, right? And yeah, so modulo that, it's the state of the art. Okay. All right. So that was mixed linear regression, right? But what about deep learning? Because that's what anybody cares about, right? So what do I mean by that? So the thing is that out of the box, you cannot really apply this to neural networks, because we are looking at the loss of training samples, right? And neural networks, depending on how you train them, the training error is 0, right? I mean, I'm sure you must have heard this, that for many popular models, the training set that they were trained on has 0 training error, right? They have fit all the data, right? And it is kind of an ongoing surprise in statistics of why is this not overfitting. It's outside the purview of our talk, right? But the way it affects us is that this cannot be applied out of the box to neural nets, right? Which was our hope initially, right? Because the training loss is 0 for everything, right? So the solution is that you should not train all the way to completion, at least initially, right? So if we were doing what I advocate, which is to kind of iterate between training the model and selecting the data set, and training the model and selecting the data set, right? Then when you're initially training the model in the initial epochs, do not train all the way to completion or convergence. Okay? So here's some empirical kind of justification of that. Right? So these are 4 different problems actually. One is image classification with random error labels. Right? So I kind of talked about it. I didn't show you any results, right? But if you have random error labels, or you have systematic error labels, or you have generative models with mixed data, or you have backdoor attacks, which I promised I'll tell you but never told you, right? Okay. In all of these things, there are 2 curves, right? There is so on the x-axis of all of these things is the number of training epochs, right? It's essentially the number of SGD steps or mini batch SGD steps, right? And on the y-axis is the accuracy on the training data itself, after I have trained the model for, let's say, 10 epochs, 20 epochs, 30 epochs. Okay? And there are 2 curves because there is the training data that is actually good and the training data that is actually bad. Right? So if you go back to my example of the horses and birds, there are 80% of the sample that are horses and 20% are birds. Right? Now I train my model for 20 epochs and I look at how many of the actually correct horses did it label as horses. So that is the top line accuracy, right? The solid line in the top left corner. Okay? The dotted line in the top left corner is the accuracy on the things that were labeled horse but are actually birds. Okay? So there is a difference in accuracy, right? That's the upshot of this thing in the initial epochs. Right? And so if you want to run trim loss, then you need to stop it in the initial epochs, right? Because there is actually still a difference. Okay.
So how do you decide that?
How do I decide what?
So till when to stop?
How do I decide? Yeah, there is no principled way to decide that.
Yeah, these 2 pictures, top 2 pictures, there seem like some kind of a jumps.
Oh yeah, okay. So a jump is just in the way training is scheduled. So there is so the way mini batch SGD works is that there is a particular learning rate for several epochs, and you can control that rate, but usually it's fixed, and people don't jimmy with it that much, right? So essentially with this, after 50 epochs, in like the top left corner, the learning rate jumped, and when the learning rate jumps, the model jumps essentially till it goes to a new operating point. Okay, so yeah, so what I should have done is cut off this thing at 50 epochs, right? Because I'm not even going to go to the first learning rate update step. Yeah. Okay, so let's go to deep image classification, right? And the algorithm is pretty clear. I'll first train a classifier on all samples, and then I'll choose the best tau fraction. Okay, so which means for every label, I will sort all the images by their empirical loss on that model, and then I will pick the lowest ones, and then I'll repeat. Okay? I'll retrain the model for a few epochs, and then I'll do it again. Okay. So here's the upshot, which is that for 3 different data sets, so as we go left to right, the data sets become more complex. First is the MNIST handwritten digits data set, which is one of the simplest. And this is for the results for a 2-layer convolutional neural net. And then there's CFAR10 with a 6-layer ResNet. And there's CFAR100, which is the same thing as this, except that it has 100 labels instead of 10, with a bigger network, right? And on the, I mean, each row corresponds to the fraction of samples that are good, right? So, so the remaining samples have systematic error. So when 60% of samples are good, then the oracle, which knew which were the good samples, gets 94% accuracy because it knows what the good samples are. So it kind of ignores the bad ones. Right? And trim loss minimization gets 90%, but the baseline is just 70%. Right? And
you say baseline that doesn't know, that just does what Oracle would have done without knowing that.
That's right. Yeah. So the baseline is the one that just ignores the fact that some labels are bad and just trains. Right? In some sense, our baseline is iteration 0 for our model, right? And as we iterate, we go to our model. I think this is after 5 iterations. So kind of the upshot here is that the observation generalizes across data sets and across models. Yeah.
But you do know the ratio, right?
I do know the ratio.
That's not a hyperparameter. We know it.
Sorry?
That's not a hyperparameter. We know it.
Yeah, we know it. Or it's a hyperparameter. I mean, right? Like in a real problem, you may not know it, right? And then you might get it wrong. Right? Yeah, so I don't know what's a good way around that, but you can have a conservative estimate, right? So for example, here the fraction of good samples, for example, is 60%. If I had assumed the fraction of good samples is 50% and still done the same thing, I would have got the same result because the data sets are actually pretty big, right? So if if the fraction of good is 60% and I assume 50%, if my data set is big enough, that's fine. What is wrong is for me to assume it's 70%, right? So I should be conservative in how much data I think is good. Yeah.
These are training errors or these are test errors?
This is test error.
Okay. Now, second question is, let's assume that sort of to these same algorithms, you fed the original data. There's no reason why one should assume the original data was good.
Mm-hmm.
Right? So one could sort of feed the same
Yeah.
the original data without bad things.
Yeah.
And then so run your iteration, your ITLM.
Run my iteration, but my iteration assumes some of the fraction of the data is bad.
But so, and of course,
Yeah.
given that you have the entire data, in principle you can just run
Yeah.
it, not the best thing to do, but
Mhm.
all sorts of fractions. And are there fractions for which sort of somehow your algorithm improves the accuracy over the?
Yeah, that's a good question, right? Which is that even if the data was clean, does my algorithm do better than not doing it?
Because clean itself is not.
Yeah. So the answer, I think, depends on the data set, right? So for these deep image classification data sets, they are actually amazingly clean, and so it's very hard to beat the naive thing, right? So like essentially what you're doing is like, there's one more line here which is 100%, right? And I didn't plot it, but essentially at that point all numbers equalize, and it's very hard to beat, right? Like I do iterations, it doesn't matter, right? So our original hope was to use this to actually find mislabeled examples in ImageNet, and we didn't find any, right? But in NLP data sets, they are much harder, right? Because the labeling problem itself is much harder, right? Like if someone shows you a sentence and says that, is this a positive sentiment or a negative sentiment, it's often not clear, right? There's irony and all that. So I have more hope in NLP data sets, but yeah, I don't have results to report. Okay, let's talk about the GAN example. Yes, sorry.
Did you try to do cross-validation for this fraction?
Classification for what fraction?
Cross-validation. Suppose you have a validation set and you do that by selecting your fraction, and does that generalize to your test?
Okay, so does my cross, so the question is that I try to do cross-validation. Is my cross-validation set a clean set?
Let's say it's a clean set.
Okay, right, so.
And you can test whether, because now you're assuming that you know the fraction, right?
Yeah, so you can try to do cross-validation to find the fraction. Yeah, that's a good thought. We have not done experiments to find out if, how that works.
And also, did you do any averaging study such that suppose you don't know the actual tau, and you just pick a random tau in your algorithm, and then just run for a variety of different fractions? Does that change it a lot?
Yeah, it changes a lot. So for example, the moment I become optimistic as opposed to conservative, the accuracy goes down significantly. Yeah, it goes down significantly. I mean, it doesn't become as bad as baseline, but it's like pretty bad. Right, yeah. So you do need to be conservative. Okay, so I told you about generative models, and the way they work is, so this thing on the bottom left is the generative model. Okay, so I put in a random vector, which is low dimensional, and I get out let's say an image, right? And the image looks like the image that like one of the images from the data set it was the generator was trained on. So how are these generators trained, right? Because the thing is that now I'm just generating samples. So the question is, what is this loss, right? So to see what the loss is, you have to see how the GANs are trained. But it's pretty obvious what the loss is once you know how the generators are trained. So the way they are trained is, suppose for now I just have clean data, right? I have a bunch of handwritten images, and I want to generate random new images that look like handwritten digits, but are actually generated, not real, right? So now what I do is I have two neural nets, right? And they are kind of adversaries of each other, right? The first one is the generator network, which takes a random vector and maps it to some image. And then there is a discriminator network, which takes in an image and does a binary classification of was this real or was it generated. Okay, and now the way these two are trained is I feed the discriminator alternating samples. I feed it a real sample and I train it to say real, and I feed it a fake sample and train it to say fake, right? When I generate a fake sample or a generated sample, the gradients for this train not only the discriminator but also the generator. When it is real, it trains only the discriminator. Okay, I mean, okay, this is like pretty classical stuff in terms of neural net timelines, yeah. So the idea is that here our theta is the weights of the generator and the discriminator. Okay, right, and L theta is the final discriminator loss over here, right? So in all my training samples, so my training samples are the ones up there, the one that says real, right? This fake stuff is not my training samples, right? My training samples are one that says real up there, and they're put through a discriminator, and it gives a loss, which is the probability of it being fake when it is actually real. Okay. All right, so this is how GANs are trained. There's the discriminator, right? And now with a mixed or spurious sample training set, what I mean is that what I think is real is actually mixed, right? So I have 80% of my samples actually being handwritten digits and 20% being this like fashion data set. Okay, but I think everything is real, right? And I follow the same procedure. All right. Okay, so this is the output for 32 random samples. This is what I said, what we saw before, right? It's kind of like low quality. Okay. All right. So as I said, the idea is to use the loss surrogate, which is the output of the discriminator. Once you do that, then the algorithm is kind of out of the box for you, right? It's like you first train a GAN on all the samples, again obviously only for a few epochs. Then you run the discriminator only on all your training samples, right? For every training sample, it will tell you if it's real or not, right? And so you run the discriminator only on every training sample. Then you choose the fraction of tau that it thinks is most real, and then you retrain with that for a few epochs, and you repeat, right? And you can increase the number of epochs you train for as you go further in this kind of iterative training process. Okay, so these are the results if you do this for MNIST and fashion MNIST, right? So here what I mean by iteration is actually the iteration of my outer loop algorithm. There is of course SGD happening inside it, right? But as far as I'm concerned, it's just updating the model, right? So the baseline is what we saw before, and then after like 5 iterations, okay, it's still kind of bad as compared to if you had a pure MNIST data set, right? But at least there are no clothes showing up, and most of the digits you can kind of imagine what the digits were, right? Both things are not true in the on the left side, right? So at least visually, it is doing the correct thing for MNIST, right? It's the same thing. So we did the same thing for a slightly more complex. Yes.
This is a confuse of like the procedure. Do you train the generator?
So in training, okay. So at any particular iteration, we have a number of samples that we think are good, right? Then I train the discriminator and the generator, like I would anyway, right?
That you choose some fraction, right?
Yeah. So yes.
But that fraction obviously could have some samples from the generator.
No. So when I choose samples, I don't choose from the generator, right? Because I know what samples I generated, right? So there are 1,000 training samples which I didn't generate, right? That's my data set, and then I train my generator or whatever. Once it's trained, I guess I could generate 10 million samples, but I never do that. I generate 0, right? I just take the discriminator and evaluate my 1,000 samples, and then select 800 of them. Okay, so this is a slightly more complicated data set where we took CFAR 10, which is the original horses stuff, and we considered that to be a bad data set corrupting celeb A, which is a data set of images of famous people. Okay, and now if you run a GAN on images of famous people who are famous because they look good for the most part, you will get a face generator which generates amazingly good looking faces. Okay, this is already known. So we took this good face generator, and we corrupted the celeb A data set with CFAR 10, right? So it's a spurious data, and this looks like pretty bad images, right? So this is a GAN which actually gives very good images, right? And so when you have a baseline, you have lots of things that don't even look like faces at all, right? And here 5 iterations is not enough, right? Because even at 5 iterations, okay, more things look like faces, at least when in randomly generated vectors, but there is still one that doesn't even look like a face yet. Okay, but the algorithm is doing something. A more quantitative measure is to see what fraction of the training set the discriminator gets right. Okay, and kind of the upshot is, since I'm already out of time almost, is even by the quantitative measure it improves. Okay, here's a failure case. If at least empirically, this approach cannot be doesn't work all the time. If I have a data set that's 90% corrupted, I cannot generate it with 10%, even with all this trim loss and all that stuff, right? So here, when you have 60% for MNIST and fashion MNIST, the breakdown point is 60-40, right? Because I keep iterating, and it keeps making a mixture of fashion images and handwritten digits. It cannot narrow down to the majority set, even though it is a majority, and even though I know that it's 60%. Okay, so this is a summary, which is that this is kind of a pretty generic approach that works across neural net applications, and also has some also provides state-of-the-art results for mixed linear regression. There's an interesting question which I'll just spend a couple of minutes on, which is to contrast, and this is more like in the realm of open problems, in the sense that I don't know how to formalize this, but I think it will be nice to formalize, right? So iterative trim loss for robustness, what is it doing? It's alternating between estimating a model from weighted samples. I guess in my talk, my weights were 0 or 1, right? Like I either fully rejected samples or fully accepted them. But you could imagine doing a soft thing where they are kind of down weighted but not rejected. Okay, fine. So modulo that, I'm estimating a model from weighted samples, and then I am increasing the weight or increasing the importance of samples which have low loss. And I keep doing this for a bit, and I finally use the final model iterate. And this thing is robust, okay, to some extent, right? As opposed to that boosting, right, what that does is it also estimates a model from weighted samples, but then it does the opposite of what I'm doing, which is it gives higher weight to higher loss samples, all right? So it seems to be doing exactly the opposite thing, right? And one would imagine you cannot have boosting and robustness at the same time. The only reason why I think it might be possible is because it uses an ensemble of all the models it generated so far, but I'm using only the last model. So I think it's an interesting question to see if one can do boosting when you have outliers. Okay, and boosting needs to be changed for this, and I'm not sure how to do it. Okay, but it's an interesting question. So thank you. Okay, sorry. We have a new kind of cross-departmental postdoctoral fellowships with a lot of my awesome colleagues and me. So the postdocs can work with all of us, and it would be, so if you are thinking of going in the academic job market and want to work with a diversity of perspectives from theory to practice, I think this would be a good option. So with that shameless plug, thank you so much for listening to my talk.